Hi, this is Pat Kelly. Okay, in this problem, they want us to verify Green's theorem. Very cool theorem. And we're going to do that by showing that these two integrals end up equaling each other. That's what Green's theorem states. Okay? And I know I'm staggered a little bit here, but we're going to show that each of those is equal to the same value. And I'm only staggered because of the work I'm anticipating doing for each of those. Okay, now, to begin, they did give us a path, of course, and I've already drawn it for us. I think in this problem they gave us those four different ordered pairs, which end up being a square. I think they mentioned that as well. So I've got my path if it helps give you a visual, which you might want, because in order to do this first integral, you're going to need one of those parametric representations. Okay, so I like to see what's going on when I write one of those. So let's write the parametric representation of this path down here, r of t function, which you can probably see is coming. It's going to be a piecewise function just across this first leg of the trip. I have x going from 0 to 1, so I'd probably just say t times I. There's no j because y stays at 0 the whole time. Let me come over here maybe and get a handle on the parameter for that branch. Let's just let t go from 0 to 1. Okay, piecewise function, and I've got my restricted domains started for the first branch. Let me finish the restricted domains for the other branches, because it makes sense to just keep incrementing by 1, I think. You know the deal. You just want to make sure that you pick up where you left off from 1 to 1, 2 to 2, and here's going to be 3 to 3. But other than that, answers may vary, okay? So I like to see these then to flesh out the other branches. The second branch is the second leg, the right side of my square. And there, the x-coordinate has to stay at 1, so I would just write that as an I vector, 1 times I, plus, in my j this time, my y needs to go from 0 to 1, so I would probably say, trying to go from 0 to 1, let's try t minus 1 times j. And always check to make sure they make sense. 0 to 1 looks good. Okay, third branch, third leg of our trip is across the top of the square. Now I want my x to go from 1 to 0, so let's try 3 minus t. I always have to stop and think on those. The I vector plus, this is the easier one, the y coordinate stays at 1, so that's just going to be a j vector. These are all vectors here. Okay, that's the third branch. The fourth branch, this is the left side of my square. The x coordinate, that's the easy one, that stays at 0. Y, I'm going to need to go from 1 to 0, so let's try 4 minus t times the j vector. I should always be checking, but yeah, 4 minus 3 is 1, and 4 minus 4 is 0. Okay, we got it. There's my parametrization of this path, which I need, because now I'm going to come up here and do this integral, but you definitely want to keep an eye on your piecewise function, because what I'm going to do is even plug in as I go. I'm confident you'll follow me. You'll be able to follow me, because I know, you know, when we do an integral like this and it's a piecewise function, you're doing an integral for each branch. Okay, so you're going to see 4 integrals coming at you to begin. I'm also confident you'll be able to follow me in the setup of these, because for the first branch, my limits are going to be 0 to 1. And then what I'm looking at is within this expression, the first part is y squared. You're in your first branch. Y is the j component, which is 0 times dx. To get dx, you're differentiating right there. The derivative of t is 1, so that's dt. But of course, that is going to blank out to 0. I still want to write it for the setup, though. I got to keep going. Plus x squared. That comes from this I component. The x was squared, so I'll square that component, x squared, so t squared. But dy is the derivative of the j component, which is 0. Okay? So that whole integral's gonna blank out to 0. I want to keep going with my overall integral, which is going to be the sum of the 4 integrals. Let me fit another one in up here. Now I'm just slipping down to the second branch. I'm going from 1 to 2. Let's go through that same setup, that same plug-in, really. Y squared, this time I do have a y, it's t minus 1. They did say squared, the y was squared. Okay, and then dx. dx is going to come from our derivative of the I component. The derivative of 1 is 0, so that's times 0. And then plus my x, which is that I component. It's 1, but squared, that's still 1, times dy. Now I'm looking at the derivative of this component, derivative of t minus 1 with respect to t. That's just 1. So this is a dt. Put square braces around that, integrand. And I'm just slipping down here to put a plus. Remember, there are 4 integrals, so let's just go to the third, which is your third branch. Go from 2 to 3. Still follow this formula. Y squared. Square the 1 that's here, so that's going to be 1. Multiply by the dx. I'm looking for the derivative of the y expression, sorry, the x expression, the I. And the derivative here is going to be a minus dt, because that t is negative. And then plus x squared. So I'm squaring the 3 minus t. And multiply that by dy. dy comes from the derivative of the j component. The component is 1, so the derivative is 0. And I'm hoping you're appreciating the zeros as much as I am. I'm going to have a lot of this work blank out in the next step. One more integral from 3 to 4. Y squared. My y component is that whole 4 minus t. I have to square it, times dx, but there is no I component there, so the derivative is 0, plus x squared, which is the 0, times, just for completeness sake here, the dy is going to come from here. It's going to be a minus 1, but there is that 0 in front of it, so we're in good shape on that one as well. Put a square brace in there. Okay, so with all that blanking out, I think I can fit an answer in here, maybe in 2 steps across, because that whole thing is 0, right? This integral, the first part of it goes to 0, and the second part of it is just a 1 dt, so the integral of that is going to be t. I do have limits of integration, 1 to 2. Let's take a look at our third integral. Second part blanks out, but the first part does have a minus dt, which will be a minus t, which I have to evaluate from 2 to 3. And then the fourth integral completely blanks out, 0, 0. Okay? One more step over, because I think I can do this in my head. Put in the 2, subtract what happens when you put in the 1. You're going to get a 1. Plus, I'm actually pulling this minus out. And then 3, plug in the 3, subtract what happens when you plug in the 2, and you're going to get a 1. So final result there is 0 after all that. Okay? And I don't think any individual part of that was too involved, just tedious. And we don't really like to get into tedium if we can avoid it. And that's the point of the second part of this problem. Okay? It's the coolness of the Green's theorem, is that these two things, these two integrals, yield the same result. And you're going to see that this second approach goes much more smoothly. All right? So let's do this one. You can see what we need is a partial of n with respect to x, also a partial of m with respect to y. Your n and your m, let me just point up here really for the last time. Your n and your n come from here. This is your n, and this is your m. So as I get into this integral, let's do those partials as we go. I left a little bit of space too. We're going to get some limits on those integrals. The partial of n with respect to x, take a look with respect to x, that's 2x, minus the partial of m with respect to y. With respect to y, that's 2y. Okay, then the dA, that's your differential element of the area that you're covering. The area that I'm covering involves both x's and y's, so I'm going to integrate this with respect to x and with respect to y. It actually doesn't matter the order here. Typically you go dy dx, it doesn't matter. And it doesn't matter because the involvement of either variable inside is the same, so no more advantage on one than the other. And also, importantly, the limits of integration are no more involved for either variable. You take a look at your square, but your x's go from 0 to 1 and your y's go from 0 to 1. Okay? All right, now let's do this double integral here. Keep the outside. And if we integrate the inside with respect to y, I'm going to get a 2xy minus y squared. I still need to evaluate that from 0 to 1 from my inner limits of integration. And once I get that, that will still be a dx. There's still a dx outside there. Let's evaluate this definite integral on the inside. I think I can slip over for that. It's not bad. I plug a 1 in for y, so this just becomes 2x. Let me get my integral going, 0 to 1. This is a 2x minus 1. And then, yeah, plug in your lower limit of integration, but that's 0, so that's going to completely blank out. That's good. Dx. And then we'll evaluate that integral. Slip over here just for a little bit more room. Integrate this with respect to x. I'm going to get x squared minus x evaluated from 0 to 1. 1 minus 1. Put in the 0, you get 0. Subtract those two 1s and you get 0. And you get the same answer. Okay? Pretty cool way to do it with the second integral, which is the cool factor of Green's theorem. All right? Go practice some on your own. You'll appreciate the coolness.